This is X1, past exam number 1, question 19. And the question here is there is one single input or one single feature, and it can only take integer values, and they are 0, 1, 2 until 10. And there are only two labels, either 0 or 1. And the question is how many possible linear classifiers are there? And if we look at the example here, these three classifiers are classifying, say, when x is less than 0.4, we're classifying it as class 1, and otherwise we're classifying it as class 0. And similarly, if we include 0.4 or not, it doesn't really matter. These two are identical because none of the features can take on the value 0.4, so it doesn't change anything whether we include it or not. And similar for 0.6, everything less than 0.6 being 1, everything larger than 6 being 0.6 being 0, it does not change the classifier because these features cannot take on non-integer values, so it's still 0 is classified as 1 and everything else is classified as 0. So if we look at all classifiers in this form, then we can say everything, say, less than 1.5 is class 1, everything else would be class 0. So in that case, it's basically 0, 1 is they are classified as class 1, every other integer they are classified as class 0. So of course, similarly, we can do 0, 1, 2, 3 is in class 1, everything else is in class 0. So there are how many of these? There are 10 of them. However, this is actually different from if we flip the sign. So for example, if we say anything larger than 0.4 is class 1, so everything there is class 1 and everything to the left is class 0. So note that this classifier is different from the one we have here, and also it's different from all the other ones that we included, because for all the other ones, 1 is on the left and 0 is on the right. So this one is also unique and it's different, and it's also a linear classifier. So we have another set of 10. So we can classify 0 and 1 as class 0 and everything else as class 1. So similarly, there is another set, so we have 10 times 2. So these are 20 classifiers that are different, and there are 2 that are still missing here. They are basically classifying everything as 0. So what we can do is say anything larger than say -1 is classified as 0. Everything smaller than -1 is classified as 1. It doesn't really matter because all the numbers must be larger than -1. So in that case, we can have a classifier that classifies everything as 0, and similarly we can classify everything as 1, which is this. So we can say if the number is less than, say, 11, then we classify it as 1, otherwise we classify it as 0. So we have 2 of these, so there is a total of 22. Okay. So the next question I want to do is question 28, which is the backpropagation question. So let's first draw the neural network. There are 9 inputs, and then it is connected with 3 hidden layers. The first hidden layer has 5 units, and the next one has 10 units, and the next one has 4 units, and the output there are 5 units again. So all of these are connected. Let's draw some of them. Yeah, my drawing is not great with these neural networks, but in any case, they are all connected. Every unit is connected to every unit in the next layer, and we are interested in W111, which is connecting the first unit of the the input layer and the first unit of the first hidden layer. So this one is the one that we are interested in, and we want to take derivative the derivative of c with respect to that W11. So c is a function of all of these output units. Okay, so the first thing is in the gradient descent formula in the backpropagation step, which means we already did the activation step, so we know all the values of the hidden units and the output units. We only need to compute a gradient, which is W11 is equal to W111 minus some learning rate multiplied by the gradient. So in particular, in this formula, we already need to know this one here. So we already are using one of the weights. And I mean, the main question is asking how many weights are we using in this derivative. So let's write it here, the derivative with respect to the W11. And it doesn't really matter whether we use stochastic gradient or regular gradient descent, they use the same set of weights. And I'll just write Ci here. If you want to do batch gradient, we can do a sum over I from 1 to n being the number of data items. Okay, so the key is write this out and count how many weights are there in this. So the first step is, of course, differentiate with respect to the O's. So the O's are these ones, there are 5 of them, and we need to sum over 5 of them. So let's say j from 1 to 5, and sum the derivative of cost with respect to each one of these output units. And then each one of these, so if you focus on only one of them, say the j's one, then this one is connected to all 4 of the previous layer units. So in particular, we have derivative oj for each one of these j's. They have derivative with respect to h in, how did I write this, 3. And let's use the index k. And k, there are 4 of them, so let's sum over k from 1 to 4. Okay, so that's the next step. And then I think you can see the pattern. If you pick any arbitrary one of these 4 hidden units, it has derivative with respect to all 10 units in the previous layer. So let's do the sum hk3 divided by, no, I shouldn't say divided by, but the derivative with respect to a, say hl2, and l, there are 10 of them, so l is from 1 to 10. Okay, so now let's look at a particular one, the h2l. If we want the derivative with respect to this weight, do I actually care about the other ones? So if we compute the derivative with respect to, say, another h1 unit, so hidden layer 1, and another unit that's not unit 1, when we compute the derivative with respect to that weight, we get 0 because they are not related in any way. So when we take the last hidden layer derivative, we only care about the first one. So in particular, we only care about this one here. And we actually care about all the next layer units connected to this first unit here in the first hidden layer, but we don't care about all the other connections. So that's why in the formula we actually do not have a sum, and we only have h11 here. And then of course h11 has a derivative with respect to this w111, and we know this derivative is just one of the x's, so it's x1, basically xi1. Okay, so now the next step is to write out which one of these contain which weights, but I think you can already see here that we need all 10 of these weights, and we need all 40 of these weights, and we need all 20 of these weights, and we don't have weights here. So at this point, I think you can already count, but let's take a further step and say this we know is x, and this we know it's the derivative of the activation, so it's g prime, and that g prime again is the derivative of the activation with respect to the linear part, so that derivative is independent of the weights. And then we multiply this by the actual weights. So these weights are from unit 1 in the previous layer to sum of the unit L in the second layer. Again, when we take a derivative like this, I think in class the notation we used is we can do dh to L with respect to dz to L, and dz to L with respect to dh11. So the z thing here is the linear part, so it's just the weights multiplied by the previous layer units and sum them up. So if we take this derivative, we would always get the weight, and if we take that derivative, remember the relationship is h is g of z, so we always get g prime, and this g should not contain any weight, so this thing is independent of any of the weights, so the weight only comes in here. And again, there are only 10 of these. So that's this partial derivative, and you can probably see the pattern here. These are again g prime multiplied by those other weights, which are from unit L to unit K, and they are in the third layer. So all of these would appear, and note the subscript. There are L from K, and there are 10 L's, and there are 4 K's, so there are 40 of these weights here. And let's move back further. So all with respect to hk in the last layer, so that's again g prime, the derivative of the activation function multiplied by the weights, and there are the weights. I think in the notation we actually start it, so we have kj. Yeah, if there's only one output unit, we would ignore the j, but here there are multiple output units, so we should keep them, and that's basically the output layer weights. So how many of these things there are? So if we count the k's, there are 10, or there are 4 of them, and if we count the j's, there are 5 of them. So there are 20 in total. And I think I mentioned here, there's only 1, and L, there are 10 of them, so it's 1 times 10. So if we sum up what we just talked about, there is 1 in the first layer, so that's just W111. And there are 10, so that from the next layer, and there are 40 from the next layer, and there are 20 from the last layer. So these are the weights that are needed in the calculation of this gradient. And if you write the whole thing down, you can see explicitly where these weights are, and you can count how many of them are inside this sum. But the quick way to do this is just to look at the diagram and know that there are only 10 units needed in in between the first and second hidden layer, and there are all 40 in between the next two layers, and there are all 20 in between the next two layers, and so on.